So now we're running the model, and you can see I've actually run it a couple times. The first time wasn't that accurate, so sometimes you may need to run the model a few times. Potentially may actually need to create more layers than you think. You can, of course, save the model, so you can improve the model's performance by saving it, rerunning it, saving it over and over again. And effectively, that's what's happening here, is that the accuracy is actually improving as I've run the multiple layers. You can see the ACC and loss. These are representative of how much information is actually being improved. So particularly the accuracy measure, you can see it's advancing, improving towards 1 as we get more and more iterations. So effectively, we have a very good model in predicting the numerical data sets, or at least evaluating the numerical data set and classifying them into the right categories. So the idea here, of course, is that the models are not only run multiple times on the training data, but the activation between the layers, by connecting multiple layers that are filtered, these layers are reduced using the filters. You have activation maps that are created by these filters, which then can be spooled, or at least put into different sort of reduction techniques that allow you to further kind of choose the most important parts of your data set. So for instance, think of a kind of pooling mechanism that allows you to choose the most informative part of a given map of data. So let's say you have a given 3x3 map of data. You can either take the mean or perhaps take the most informative value or the maximum or minimum value. There's different methods in which you can apply. And then from that, you can then determine or recreate that data set in the next layer, which could then be further analyzed, and so on and so forth. So what we're doing is effectively a kind of reduction technique that tries to find the most informative data in your image and analyzes it through many different layers, piece by piece. So taking a large image, let's say, or an image, piece by piece, you break that image down, so the colors, the lines, the shapes, whatever it might be. You break those down into layers, and then you analyze that through the set of filters that you apply, eventually reducing each of those layers into the most informative parts, and then you finally put them all together at the very end of the CNN network. And then you represent the image and classify it in that regard to your problem set. So you try to say how accurate it is relative to something else that you're evaluating. And that gives you the accuracy measure. So that's effectively what we've done. You can see here at this point now the model is beginning to top out at roughly 98% accuracy, which is pretty good, considering that the model had no information about the numbers and what they were at the beginning. So what this model has done successfully is learn from each iteration and try to effectively classify the numbers from images, from pictures, and determine how similar they are to specific digits, values of between 0 and 9. Okay? So that's what we applied this week in the CNN algorithm, and we've compared this to the Boltzmann one that we applied earlier, and we can see that the CNN effectively is a much more intensive model in that it takes longer time, but it is actually generally produces higher, more accurate results in that it can apply multiple layers, convolutional layers, as well as pooling layers that apply different activation techniques between the layers to effectively reproduce and compare images to classify from one type to another, which allows us then to compare the results between this and, of course, the Boltzmann technique that we applied earlier to determine that's roughly this method is generally more accurate and also can produce better results in terms of its sensitivity to what's there. So that's basically what we've done this week, is apply these two sets of models as examples of deep learning. The Boltzmann technique is relatively faster, usually, so that's one potential benefits. However, the CNN is actually much quicker when you're dealing with more complex data. So we often people have often more and more applied this kind of modeling to large-scale data sets. So think of Google Images, for instance. That's one example where CNNs are actually used to retrieve image data that you might be searching for on Google, for instance. Okay, so that's all for this week. I hope you enjoyed the class, and I hope you enjoyed this kind of brief overview of deep learning using Python. We'll be back more, hopefully next year, with some more examples and new kinds of applications using Python.